Hello and welcome to another Ginger Mathematician video. Today we're going to go through all things A-level maths paper 5. So you've got stuck on this quite tricky paper in your first foray into statistics, then this is the video for you. We're going to be looking at lots of different parts of it: normal distribution, discrete random variables, and permutations and combinations. Again, if you need any more detail in any section of this video, then please do let me know. Right, let's get started. Okay, and on to our section on permutations and combinations, a topic students often find difficult on the paper 5. Now, we need two techniques in order to help us with the following questions, which your calculator can help you with. The first one here is this factorial sign. Now, most people think it's an exclamation mark. I'm just shouting out X, but in reality, it's an actual operation we need to understand, this exclamation mark here. So imagine I have A, B, C, D, and E. So I've got those 5 letters, and I want to find all the different ways I can put them in order. Well, if I take the first slot here, there are 5 different letters I can put in that slot. Then in my second slot, I've already used a letter, doesn't matter which letter I cross out here, and then I have 4 letters left. Next one, that's going to be 3 letters left, 2 letters and 1. So to work out the amount of combinations available here, we do 5 times 4 times 3 times 2 times 1. Now, generally in mathematics, we don't like to write things out very, very long. So we use this short notation here, this exclamation mark, to represent this. So to represent 5 times 4 times 3 times 2 times 1, we just use 5 factorial. And your calculator can do this for you. And in this case, this would be 120 different combinations. So there's 120 different ways of putting these in order, these letters in order. Notice I could do A, B, C, D, E. I could do E, B, D, C, A. If I went through every single combination, that's a lot of them, there would be 120 in total. The second thing we're going to use here is this button NCR. So you'll see NCR. Generally, we'd write that slightly differently when we write it out. I generally write it like this. What does this actually mean? So let's put an example here. So for example, if we had 12C5, what this means is out of 12 objects, how many ways are there of choosing 5 of those objects? Now, if I do an example here, if I do 4, choose 2, for example, so say I've got the objects A, B, C, and D, how many pairs can I make out of A, B, C, D? Well, I can make AB, AC, AD, BC, BD, and CD. So notice in this case I make 6 different combinations. Notice that CB and BC would be essentially the same combination, and the calculator allows me to actually work this out and work out that there are 6 different pairs that I can do from a selection of 4 different objects. We're going to be using both of those facts to help us with the following questions. Okay, so on to question 1 here. Find the number of different arrangements for 8 letters, or the 8 letters in the word deceived. Let's not get deceived in this particular question, in which all 3 E's are together and the 2 D's are together. Okay, so the way I would do this, normally we just write out all the slots. So D, E, C, E, I, V, E, D. So those are our different slots: 1, 2, 3, 4, 5, 6, 7, 8. The way to go about this is actually to combine slots together. So I have 3 E's together. So imagine I take these 3 here, or it could be any 3 I want, as long as they're next to each other. And I imagine that's now one particular slot. So we're not going to worry much about what actually goes on inside them at the moment. And if I take my D's together, again, you could take any 2, as long as they're next to each other. Okay, that now combines as one particular slot. So actually, I've got here 1, 2, 3, 4, 5 different slots. And remember, we did this in our pre-knowledge here. If I've got 5 slots, then that means it's going to be 5 factorial. That's that weird button we've seen before. 5 times 4 times 3 times 2 times 1. Again, I'm going to show you now the calculator and how you'd actually work this out. So here's my calculator. I've got these buttons ready here. If I want to work out 5 factorial, I click on 5 and I click on the factorial button, press execute, and I get 120. So I can pop down 120 arrangements to get my 2 marks. The key thing here in this question is that the 3 E's are together and the 2 D's are together as well. We're going to see a question a bit later on where it's not so straightforward. On to question B, which takes a bit more understanding here. Find the number of different arrangements of the 8 letters in the same word, deceived, in which the 3 E's are not all together. Okay. So first of all, we want to work out the total amount of different arrangements. So this is how we start before we do anything. So the way that we work this out, if we actually pop in our slots here, so D, E, C, E, I, V, E, D. So we have those different slots here, and we want it 3 E's are not all together. The way we'd work this out is I've got 1, 2, 3, 4, 5, 6, 7, 8 different slots. So I have 8 factorial. However, notice, say I had an E here and an E here. If I swap these over, that would still be the same arrangement because the E's look identical. So that actually we've counted out too many. Now, how do we actually remove those combinations? Well, now we divide by the amount of repetitions by the letter. So notice here we have 3 E's in the letter and we also have 2 D's. So I want to remove the slots for 3 E's, that's 3 factorial, and the slots for D, that's going to be 2 factorial. So we have to be a little bit careful here. Notice each letter doesn't appear just once. There are some repetitions. The way to discount those repetitions is by dividing about the number of slots up here. Now, if you pop this into the calculator, so we've got, and let's get the fraction button out here. So 8 factorial divided by 3. Let's go downwards. There we are. 3 factorial times 2 factorial. Excuse me. And that's going to give us 3,360. So what we're saying here, the total different arrangements for all the possibilities, if you move all these letters around, is 3,360. Okay, now why is that important when we're trying to find when the 3 E's are not all together? Well, sometimes there's a more positive and negative way of actually finding the answer. What I'm going to do here is actually work out the arrangements where the 3 E's are together, because this is generally easier to do. If they're bounded together, it means it's easier to work out. So we're going to work out the arrangements where the E's are together, and then we're going to use our 2 answers after that. So imagine I go back to my slots here. So what I have is I've got 1, 2, 3 E's. So if I put a box around them, how many actual slots do I have here? Now this counts as 1 slot. Well, 1, 2, we now have 3, 4, 5, 6 slots. So we have 6 factorial because I bounded all those E's together so they stay together at every point. However, we've still got the repetition of D's, okay, because we haven't counted those. Notice I've had a D here and a D here, and I swapped them. That would still be the same arrangement. So we need to discount those, and the way that we do that is by dividing by 2 factorial, because we have 2 D's in our question. And this will work out, when we do this on the calculator, the amount of arrangements where the E's are together. So we pop in 6, we get our fraction button out here, 6 factorial, and we need to go back to our buttons here. Perfect. So 6 factorial over 2 factorial, and that gives us 360. Now let's think through the logic of what we actually want to work out here. We want the 3 E's not together, so let's just write that in. Well, if we have the total arrangements for everything that's possible, and we take away when the 3 E's are together, then by definition, everything left will be combinations where the 3 E's are not all together. You might get 2 and 1, you might get 1, 1, 1, all separated out, but each combination or each arrangement will essentially not have the E's together. So all we do here is we take 3,360, we then minus the 360, and that's going to give us 3,000 different arrangements with the conditions that's given in the question here. Perfect. So you can have a look at the mark scheme here. Again, it's not very helpful. I find this video in particular is going to be really helpful for you understanding where this number 3,000, where this number 120 actually comes from. Okay, on to question 2 here. So this is a different style of question. If you're finding this video useful, by the way, then please do like and subscribe so more people can understand this quite difficult topic about permutations and combinations. So there are 6 men and 8 women in a book club. The committee of the club consists of 5 of its members, and Mr. Lan and Mrs. Lan are both members of the club. And the first thing that we need to do here, and this means we have to read the question carefully, how many different ways can the committee be selected if exactly one of Mr. Lan and Mrs. Lan is on that committee? So exactly one, not both, okay, not at least, but exactly one. So we have 2 situations here. We have a situation where Mr. Lan is on the committee, and then we have 4 other members of the committee. And we have a second situation where we have Mrs. Lan on the committee, and then 4 other people. So what I want to do from these 4 slots that are remaining, I've got, well, let's have a look here. We have 6 men and 8 women. I've already selected a man here, and I don't want Mrs. Lan in there as well. So normally we have 14 people. We're discounting Mr. and Mrs. Lan because they can't both be there. So we've only got 12 people remaining to fill those particular slots. I can't use Mr. Lan or Mrs. Lan for either of these situations apart from the one that's already there. So essentially I want to fill these slots up. I have 12 people available. Again, I want to choose 4 from them. So I need to work out 12 choose 4. And that's going to be the same whether it's Mr. Lan or Mrs. Lan. So now I'm going to show you how to use the calculator to work out this 12 choose 4, choosing 4 people from a collection of 12 people. Okay, so we're going to use this button here, the NCR button. So we go 12, and then we click on F3 to give us the C4, and then it will tell us the answer here of 495. Notice we have 2 situations here, one for Mr. Lan, one for Mrs. Lan. So if we add those together, so total is equal to 2 lots of 495, and that's going to be equal to 990 ways. The key thing about this question was the exactly one of them. So we can't have both on the same committee, hence why we're choosing from 12 people and not 13. On to a trickier question here. So in how many different ways can the committee be selected if Mrs. Lan must be on the committee? So let's draw a diagram out. Here's Mrs. Lan. She's on the committee. And we've got 4 other slots available now. And there must be more women than men on the committee. Now we already have a woman on the committee. So we've got a couple of situations we can consider here. Situation 1. We have Mrs. Lan, who is a woman, and we could have all women on the committee. So you have 1, 2, 3, 4, and then for these 4 slots, so we ignore Mrs. Lan because she's already chosen. From these 4 slots, they all need to be women. Or we could have a situation where Mrs. Lan is on the committee, and we have 4 slots, and in this case we have 3 women and 1 man. That still gives us a majority of women on the committee, 4 women and 1 man. And our third situation is Mrs. Lan is still there. I'm sure she's loving the committee at this point. We have 4 slots, just like so, and we have 2 women and 2 men. Notice there is still a majority of women. There's still 3 women and 2 men on the committee. So how do we actually work out these combinations? So the first one here is we have 4 slots. Notice we have 8 women normally in the book club, but we've already chosen Mrs. Lan, so we have 7 to choose from, and we need to choose 4. So that's our first option, 7 choose 4. The next one here, well, we have 7 women, but we want to only choose 3 of them, and then we have 1 man to be chosen from the other 6 people. So 6 choose 1. I want to choose 1 man from that collection of 6 men that are there. Then if we do the last part, we have 7 choose 2. So we want to choose 2 women from the 7 women that are available. And then we want to choose 2 men from the 6 men that are available. So we need to work out all 3 different situations here. Now I'm going to take my calculator next to me to work these out for you. Now you've seen how the calculator works. So 7 choose 4, that's equal to 35. Then we have 7 choose 3 multiplied by 6 choose 1. The reason we're multiplying, if you've wondered this, is essentially a probability. So probability of 3 women and 1 man, hence this multiplied here. And then if we do the last part, so 7 choose 2 times 6 choose 2, that's going to give us then 350. So we've worked out all the possible ways of doing it, so we just need to add those up. So if we total 35, 315 and 210, so we add those previous answers together, and we get 560 different ways. Sometimes you'll just need to break down that problem into all the different scenarios where these things can happen and then add the results together. Notice drawing a diagram like I've done here, it's really going to help you have a good understanding and get all those 4 marks. So you can see the answers here, so 990 from before and 560. Again, go through the mark scheme. It's getting late. Go through the mark scheme to make sure you're happy with what we have done here. Okay, and on to section 2 of this video, where we're going to look at representing data. I've picked out 3 questions here. They're all slightly different, but going through the key topics you need to know for the paper 5 for stats 1. So we have the times taken to travel to college by 2,500 students summarized in the table below, and we need to draw a histogram. Okay, important topic on this course. As soon as you see the word histogram, I'm thinking to myself, I need to be talking about frequency density. That is the phrase that is linked with histograms. And in order to work out the frequency density, there is a formula that you need to know, which is the frequency density is equal to the frequency divided by the class width. So you need to know this formula as soon as you see histogram. This is the formula that should be going through your mind at this point. So let's work out the frequency density for our table. So generally what I do here is just add an extra row or extra column so we can put these in and work out the frequency density. Now make sure you've got your calculator for this video. We're going to be using it a lot compared to some of the pure maths videos that we have done. So we want to work out frequency density, so frequency density, and then we use our formula. So frequency is 440. So I'm going to do 440 on my calculator divided by the width of this. So 20 minus 0 is 20. So I'm going to do the calculation of 440 divided by 20. Now again, you need to have your calculator ready for these calculations. Again, please don't do these things in your head. This is why we have the calculator there. Here in this case we get the answer of 22. So we pop in 22 here. For this one here, well, we've got a frequency of 720. We want to divide that by the width here. So 30 minus 20 is 10. And this one I'm going to do in my head. So 720 divided by 10 is 72. And we do the same process on each of these. So this would be 920 divided by 10 as well, because 40 minus 30 is 10. That gives us 92 here. Notice this is slightly different, so you have to be careful with these questions. Notice we've got a width of 20 here. 60 minus 40 is 20. So then we do 300 divided by 20. So be careful, keep an eye on those widths, and that gives us 15. And then the last one, this has got a 30 width here, so 120 divided by 30, that's going to be equal to 4. So the most important thing, first of all, for a histogram question is making sure we have those frequency densities. Now we're going to plot this on a histogram. So if we have a look at our scale here, we need to go up to 92. Remember, frequency density is going to be written on the y-axis here. So we need to go up to 92. So I think we're going to go up in 20s here. So 0, 20, 40, 60, 80, 90. I think that's going to be fine. So again, you need to use a ruler for this, of course. I'm going to try and do this freehand, which is not a great idea on a computer, but we will be fine. So let's pop in that scale here. So we start at 0. We're going up in small ones, we're going up in 10, so 20, 30. And just making sure you take your time. Again, there's a lot to do in a stats exam. We want to make sure we're being as accurate as possible. And we only need to go up as far as 100 for this part here. Along the bottom, that's going to be our time taken. So I'd write here. Oh, it's not liking that. Okay, let's pop it over here. Time taken. That's going to be in minutes. And then we go across. So we also go across to 90. So the same scale, I think, is going to apply here. So we go 20, 40, 60, 80, 90. You don't need to go any further than 90. And again, we pop in this scale. Again, we can go in 20s. Or you can put 10 in there as well. That's perfectly fine. So 60, 80. I should probably put the 10s in there as well. Just running out a little bit on space here. So, like so. Right, now we need to put in the actual frequency density chart essentially here. So the frequency density diagram and histogram. So what we do here is we've got a 22 here, and we're going between 0 and 20. So we go 0 to 20. We're going to go up to 22. Now these small squares here are going up in 2s, 22, 24, 26, 28, 30. So we just need one of those. Then we put a nice straight line across. Obviously you have a ruler at home. And down like so. Now because it's a histogram, again the bars are going to be next to each other. There are no gaps here. So we have 20 to 30, 72. So let's mark on 72 here. So we're going to have a line that goes across to 30. So again, you have to look at the scale carefully. 20 to 30. And then we just pop in with a nice straight line. That is not the straightest line I have seen. Okay, down we go. Making sure to be accurate as possible. Again, if you've got a ruler, this makes life a lot easier. Cool, so we've done this one and this one. So 30 to 40 goes up to 92. That's going to be our highest point here. So we've got 30 to 40, just a 10. And then we're going to go all the way down, like so, to give us, to 40. Then we've got 40 to 60 at 15. So 15 we need to be a little bit careful with, because we've got 10, 12, 14. So it's going to be halfway in between, and that goes across to 60. So halfway across that box, and then down with a nice straight line. And then last one, 60 to 90 is at 4. So we've got 2, 4, and we need to go across to here. Notice how I'm doing this. I'm drawing in points, and then I'd use a ruler to fill that in. And we finally got our filled in histogram here. So making sure we've got all the correct lengths. I'll show you the answer here. So you can see I've drawn this as accurate as possible. Again, I've got all the key things here. I've got my scale. I've got the labels to the histogram as well, the bars, the correct length, and my frequency density, giving me then all 4 marks on that particular question. Okay, and on to part B here. So from the data, we're actually told what the mean value is here, or the estimate of it, which is 31.44. And from that, we need to work out an estimate of the standard deviation of these times taken to travel to college. So before we start anything here, as soon as I see standard deviation, I need to know about my formula sheet here. So you notice I've marked in exactly which section that we need here. Now we're looking at group data because it's from 40 to 60, for example, with our categories. And generally it's easier to use this second formula over here. So this is the square root of the x squared times f, I'll explain all of this in a moment, all summed together, divided by the sum of the frequencies minus the mean squared, and then all square rooted at the end. So let's see how we can actually use this. Before I start anything, I'm going to be writing this formula down, so I have it here as reference. So just copying it across from the formula sheet. Showing the examiner I know exactly what I want to use here. Now, before we do anything here, we do need to work out a value for the time taken minutes that's kind of sensible, it's kind of useful. And the way we can do that is work out the midpoint. So we're going to work out the midpoint of each of these categories so that we have an x value to work with. So halfway between 0 and 20, that will be 10. Halfway between 20 and 30 is 15. Again, the way you can do this is 30 plus 20 is 50. 50 divided by 2 is equal to 25. And this is why you should always double check these things. 30 to 40, that's going to be 35. Here, that's going to be 50. And this here will then be 75. These, from the formula point of view, are our x values. So we'll talk about that in a moment, whereas of course these values stand for frequency, F for frequency, it makes a lot of sense. So how do we actually use this formula to work out the standard deviation? Well, we're going to need to leave ourselves a lot of space here to make sure that we do this nice and accurately. So got a square root ready for this calculation. So the first part here is we need to work out the x squared times f's and then sum them together. So what does this mean? So first of all, we take the midpoint, the 10, we square it, and then multiply it by the frequency. That's what's meant by x squared times f. And then we're going to do the same thing for each category. So we take the x term, the 25, we square it, times it to 720, and we add all these results together. So 35 squared times 920. You need to write this out for your exam, just so the examiner has seen this. So 50 squared times 300, and then the very last one here, so that's going to be 75 squared times 120, and that's going to be all divided by the total frequency. Remember, this summation sign just means the sum of or total of the frequencies. Now we're told that in the question there are 2,500 students. So we pop that on the bottom, and then not forgetting to minus the mean squared. Now we're told the mean in the question, 31.44, so we need to do 31.44 squared. Now I've shown the examiner exactly how I'm going to go about doing this. It's all up to the calculator to do this correctly. Okay, so make sure you've got your calculator ready. Again, this is going to take a while, but it's worth watching this process at least once, seeing exactly how I'm taking very good care, putting the right values in and not making a mistake. So, first of all, we need to pop in a square root and fraction, and now we need to pop these things in. So we have bracket 10 squared times 440 plus open bracket 25 squared times 720 plus 35 squared times 920. Again, checking all the values as you go along, not making a mistake. So 50 squared times 300, almost there, plus 75 squared times 120. Probably in the exam you don't have that sort of confidence that you've definitely got to the right answer. 2,500 at the bottom, and then we need to minus the mean square. Don't forget this step. Many students do. 31.44 squared. And we press our equals button here, and we get our answer of 15.16, which I'm going to write down here. So 15.16 dot dot dot. And generally we round these things to 3 significant figures. So we get 15.2. Again, I'm going to make it very clear to the examiner, I'm rounding this to 3 significant figures. On to part C here. So in which class interval does the upper quartile lie? Okay, now as soon as I see upper quartile, I'm thinking 3/4 of the data. And if it's a lower quartile, that would be 1/4 of the data, upper quartile 3/4 of the data. So if we take the total amount of data here, we have 2,500, that's our total. So on my calculator, I would work out 3/4 of 2,500. Again, we can just use a calculator to do this. So 0.75 or 3/4, so that's 2,500. That's equal to 1,875. So we're looking for the 1,875th value, where that lies. So if we add along here, well, I've got 440. Then we add another 720, so that gives us 1,160. Not quite by 1,875. And we add on another 920 here, that gives us 2,080. Okay, so this 1,875th value lies in this category, lies in the 30 to 40 category. So again, I can just write that as my answer here. Making sure we've got the inequality signs correct for our 1 mark. And part D here, it was later discovered the times taken to travel to college by 2 students were incorrectly recorded, the classic incorrection in the data. One student's time was recorded as 15 instead of 5, and the other's time was recorded as 65 instead of 75. Without doing any further calculations, state with a reason whether the estimate of the standard deviation in part B will be increased, decreased, or stay the same. Well, it was recorded as 15, but it was actually 5. Notice that doesn't actually change anything here. If I had a time of 15, I'd still put it in this category, or if it was 5, I'd still put it in this category. Likewise, if we take 65 instead of 75, we have the same reasoning. So if it was a 75 value or a 65 value, we'd still put it in the same category. So notice the standard deviation would stay the same, as there are no change in frequencies here. You'd still put them into exactly the same category as you would before. So no change in frequencies. Okay, to get the 1 mark. Again, 1 mark, you just need the answer, so stay the same, increase, decrease, and then a very quick reason why. So you can have a look through the mark scheme here. So this is the question 3A on the histogram. And then we've got 3B here. So 15.2 for our answer. They put data is still in the same intervals, frequencies unchanged. I used this answer instead. Again, both will give you the single mark there. Okay, and on to question 7. So we have the heights in centimetre of 11 basketball players for 2 clubs here, the Amazons and the Giants. So pretty big players here. As you can see, we have the data below. And we need to state an advantage of why a stem and leaf diagram would be better than a box and whisker plot to actually show this information. And as soon as you get this stem and leaf versus box and whisker plot kind of question, notice for a stem and leaf diagram, it does actually display all the data. One of the issues with a box and whisker plot is that you know what the median is and lower quartile and upper quartile, but you don't actually get to know all the different individual data points for the particular data you're presenting. Now we need to use the data above to draw a back-to-back stem and leaf diagram. Again, a key skill on this paper, it's one of the really easy marks you can get here, so making sure you're getting all 4 marks is really, really important, with Amazons on the left-hand side and then Giants on the right. So the first thing that we look at here is what will be our stems. Well, looking at the very smallest number here, we have 178 here, 175 here. So I would go with the stems here of 17, working upwards. So we have 17, 19, and 20. We also have a 21 here, the very biggest, at 215 centimeters. That's pretty big for a basketball player, but it can definitely happen. And what we're going to do here is then we're going to construct our back-to-back stem and leaf. Amazons we want on the left-hand side, so I'm just going to write Amazons to remind myself here, and then giants on this side. And now we're going to sort of work outwards. So we first of all focus on the Amazons. The only 171 I see here is an 8. So I'm going to pop an 8 here, cross it off as I go along. Then we've got the 8s here, so 181, 182, 184. So 181. Notice I'm crossing it off as I go. That really helps me keep track here. Then we have the 190s. So we have 0 and 6. So 0 and 6. Cross those off. Then we've got, I got 8 as well. So let's cross that off too. Then we have the 200s. So we have 1, 2, and 5. Again, crossing those off as we go. And then 215 will be the 5 here. So notice I've just been taking my time very steadily through it. I would also check here, do I have 11 numbers? 1, 4, 7, 10, 11. I do. So 99% of the time here, I know I've got the right answers. Now we do the giants here, who are slightly on the smaller side. So we have 175 first of all. Cross that off. Then we have the 80s. So we've got 182, 4, 7 and 9. In fact, these are in order, so that's kind of helpful. So 2, 4, 7, 9. Then we have 2, 3, 5, 5, 5. Cross those off, and then we have 204. Okay, we check the numbers here. So we have 4, 5, 10, 11. Yep, I've got 11 values there. Notice we go to the answers here. And notice how it's structured, working from the small on the inside, then working outwards. One thing we also need to put down is a key. That's really important. So if we put down, for example, 18, we put a 4 and a 7. That means then the Amazons is 184 centimeters. The giants here at 187 centimeters. So again, really important to make sure you've got all the detail here. You've got the correct side for giants, correct side for Amazons, the right stems in the middle, and a key, because you want to be getting all 4 marks on here. Notice key here, correct giants, correct Amazons, correct stem. Can also be upside down as well, but I try and go from the smallest to largest in the middle there. Now from here, we now need to work out the interquartile range of the heights of the players in the Amazons. So remember, interquartile range is the upper quartile minus the lower quartile. Again, that's a formula you simply need to know for this exam. If we have a look then, so we've got 11 basketball players. So to work out the lower quartile, we do 11 plus 1, divide that by 4. That's going to give us the third value. So if we look at our stem and leaf diagram, we're looking for the third value. So 1, 2, 3. So that's going to be 182. Upper quartile, the easiest way to calculate this is 3 lots of the lower quartile. 3 times 3 is 9. So we have the 9th value that we are looking for. Again, we do the same process. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That gives us then 202. And then to work out the interquartile range, we then just do 202 minus 182, giving us the value of 20 to give us the 2 marks for that question. Okay, and on to question D. So a nice little twist here. So 4 new players join the Amazons team here, and the mean height of the 15 players is now, so with these 15 all included together, is 191.2 centimeters, and the heights of 3 of the new players are 180, 185, and 190. And we want to find the height of the 4th new player. So the first thing I'm going to do here is let H be equal to the height of this new player, or the 4th new player. And I'm going to set up an equation here using the information that I have. So if I go back and add up all the Amazons players, so we have 178, plus 181 plus 182 plus 184 plus 190 plus 196 plus 198 plus 201, 202 plus 205 plus that huge player at 215. Adding on the other three players that we know, so that's 180 plus 185 plus 190. That gives us 2,687. So the way I'm going to formulate this equation is as follows. The total height of the 14 players is 2,687. I add on this extra person that I don't know their height. Now I have 15 players in total, so I take that total, divide it by 15, and this will be equal to the new mean, which is 191.2. So notice from there I've managed to generate an equation that I can work with. Now we want the h on its own here, so we multiply by 15 on both sides. This cancels, giving us 2,687 plus h is equal to 191.2 times 15, and then we take away 2,687 on both sides to give us then the height on its own. Pop this into the calculator, so 191.2 times 15 minus the 2,687. I'm getting, and it's always a good sign when you get a whole number here, h, so the new player is going to be 181 centimeters tall. And that will then give me the 3 marks available. So have a look through the answers so you can see what I've been doing so far. Again, on that last question, there's lots of ways of doing it. Again, I've taken this approach here down the bottom, but again, plenty of other ways of working out to the same thing. Okay, and this question here, question 1, again, we haven't looked at cumulative frequency too much in this video, so I wanted to at least conclude one question. We have to do some interpretation here. Again, if you want to go back to the iGCSE maths style questions to really get up to speed of cumulative frequency, then do check out the video above. So we have 160 sunflower plants are measured and given on the cumulative frequency curve. Remember, cumulative frequency just means a running total. As long as you remember that phrase, the questions will make more sense. And we need to use the graph to estimate the number of plants with heights less than 100 centimeters. So I go along to 100 centimeters on my graph, halfway between 80 and 120. Again, I'm just going to go upwards here, dot, 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 dot. With a ruler, this is much, much easier. And then we go across. And notice our value here is 60. So we're going to have 60 that are less than 100 centimeters. If the question asked more than 60 or more than 100 centimeters, that would then be equal to 100. We're looking upwards, not downwards. So here the answer is just equal to 60 centimeters, just like so. And use the graph then to, sorry, not 60 centimeters, just 60. Use the graph to estimate the 65th percentile of the distribution. So what the question is essentially asking here is we need to work out 65% of the total distribution here, which is 160 sunflower plants. So again, you can use a calculator nice and quickly here to work out 65%. So 0.65 times 160. That's going to be equal to 104. So we want to work out at 104 what the length of the sunflower plants will be. So here we get our pen out. Again, we're going to find 104. Now the scale here is a little bit more tricky here. So again, let's look very, very carefully. So it's going up in twos. So it should be this one here. So 100, 102, 104. Again, accuracy is the most important thing here, because there's not much room for error. Notice that always make it hit the line. That's really important. So notice it does hit the line here. Exactly. And now we just drift downwards really carefully, making sure to follow the exact line that we need to be on. You can see my concentration here. Just be really, 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 really careful. Okay, so we've got to here. I'm making that 100, and let's have a look. So our scale at the bottom here, it's going forward, so 124, 128 to 136. Again, just double check this. 124, 128, 132, 136. So our answer here will then be 136 centimeters. Again, you only get the mark if you put exactly 136 centimeters here. And the last part is using the graph to estimate the interquartile range. Now we've seen that already here. So interquartile range is the upper quartile minus the lower quartile. So if we have a look at our data, we have 160 here. So lower quartile will be 160. Now you should plus 1 really here, divide by 4. Again, we're looking for the 40th value, or the 40.25th value, strictly speaking. So if we go across the 40 here, again, all the lines should line up very nicely. They do that on purpose in these exams, so we go 40 along until we hit the graph, which is here. Again, making sure this is as accurate as possible. I think I'm getting 76, yep. So 76 here for the lower quartile. And upper quartile, the easiest calculation here is just 3 lots of the lower quartile, which is equal to 120th value. Again, we do the same process. Let's use different color here. Let's use green. So 120, again, we go all the way across. Should be a little bit more than 120 for the same reason I gave before. But we go across. Yeah, it's going to be this line here. And then we go all the way down. Again, with a ruler, much easier. See, I'm trying to keep on that line as much as I can. Without a ruler. No pressure, I know. There we are. I think it's there. So let's have a count of this. So 140, 144, 148, 152. Or was that just before that? Let's have a look. So 136, 140. Yeah, it's probably just before it. Yeah, again, it's just before it here. So it should be at 150. Again, I've done this quite as accurate as I hoped. So that's 150. And then we then go up. Interquartile range is 150 minus 76. Again, just use a calculator at this part. Again, there's a lot to do in this particular exam, so we get our interquartile range of 74. Again, you can have a look here. Again, they give you some leeway for the upper quartile minus lower quartile. So I think I had 152. That would just about be okay. But really try and be as accurate as possible. You don't want to rely on those ranges of values when you're actually working this out. Okay, and on to the probability section of this video. Again, it's all about reading the question and being very careful when you construct your tree diagram as we go through. So Janice is playing a computer game and she has to complete levels 1 and 2 in order to finish the game. She is allowed at most 2 attempts at any particular level. So as I read through the question, I'm going to construct my tree diagram so I have the situation represented. So for level 1, the probability that Janice completes it at the first attempt is 0.6. So I'm going to draw this in. So here's my tree diagram. So this is level 1. So we can either win level 1 or lose level 1. The completing at the first attempt is probability of 0.6. Therefore, losing must be 0.4. Pairs of branches add up to 1. If she fails at her first attempt, the probability she completes it at the second attempt is 0.3. So if we take the loss and then we do our next branch here, we can again either win or lose. And completing at the second attempt is 0.3, so losing is 0.7. So we've done this part of it. If she completes level 1, she immediately moves on to level 2. The only way to get on to level 2 is either winning straight away or winning on the second attempt. Notice we're not going to continue this part of the diagram any longer. She's lost twice. She can't go on to level 2. For level 2, the probability that Janice completes it at the first attempt is 0.4. So regardless of whether whatever happened in level 1, we take level 2 as a separate situation. So now, if you won the first one, the probability of winning the second one is 0.4, and then losing is 0.6. And if we take that particular turn, if she loses that, which is perfectly fine, then at the second attempt, she would then win that at 0.2. So we've got win-loss, and this can be 0.2 and 0.8. Let's go down to the previous situation, so where she won on the second attempt but still got onto level 2. The probabilities are going to be the same. So after that loss and win, the probability of winning losing is going to be 0.4 and 0.6. And if she does lose, again, it's a bit unlucky, you lose the first attempt on level 1 and the second attempt on level 2, that's still allowed because you can try a second attempt then on level 2. Again, the probability is 0.2 and 0.8. So notice as I'm going through the question, I'm writing in my tree diagram so I have something to work with for parts A, B, and C. And first of all, we need to show the probability that Janice moves on to level 2 is 0.72. Now, the only way that she can move on to level 2 is either winning immediately, so the 0.6, or she loses and then wins. So she can either win straight away, or she can lose and then win. That still gets you on to level 2. Remember, as we're going along the branches, so if we get the highlighter out here, so she loses and then she wins. These probabilities are the 0.4 and 0.3. We're going to multiply together, so we get 0.4 times 0.3. And these are the only two situations where she gets on to level 2. So if we work this out, we get 0.6 plus 0.12. It's one of these lovely show that questions. So we do get 0.72. All is good, and we get that 1 mark. Now, the reason we set this up is when we do more complicated questions, B and C, we have a structure to work with. So we now want to find the probability that Janice finishes the game, so i.e. completes level 1 and level 2. So let's go through all the different situations where this is possible. So we'll start off first of all with win-win. So she can win the first one, win the second one, no losing in between. So this would be then the probability of win-win. So that's going to be 0.6 times 0.4. So that's our first possibility. Then we could do a win, then we could do a loss and then a win. So working through it, let's get the highlighter out. We can win the first one in level 1, into level 2, we lose the first, but then we win the second. So we're doing here let's get the pen out, a win, lose, win. That also allows to finish the game. So we get 0.6 times 0.6 times 0.2. Okay, so our next situation is that she loses the first and then wins twice in a row. So we have a lose, win, win. The reason I'm doing it this way round, if you wondered this, this part of the video, it's going to help us a lot with part C. So lose, win, win, we have 0.4 times 0.3 times 0.4. And then we've got the longest version possible. So that is if we have a lose, win, and then lose, win again, because that's still allowed. So we have lose, win, again, we're just multiplying the probabilities. So we have 0.4 times 0.3 times 0.6 times 0.2. If you're wondering where those numbers are coming from, let's get the highlighter out, different color this time. Let's go with pale green. So I'm going through, that's not pale green, that's definitely a yellow. Here we are. So lose, and then we win into level 2, and then lose, and then win. And then we finish level 2 there. So this is where these numbers are coming from. So we've got all the situations where she finishes the game. At this point, all we just need to do is add these together. So the first one is going to be 0.24. The second one, again, use a calculator. You have it there. No reason why not to use it. I generally stick to decimals for A level. It'll keep things straightforward. And next one, 0.4 times 0.3 times 0.4. That's equal to 0.048. And then the very long one, 0.4 times 0.3 times 0.6 times 0.2. That gives us a very small decimal of 0.0144. So the probability that Janice finishes, so let's pop this all together and make sure I get all 3 marks on this. Even if I make a mistake, I can still pick up 2 method marks. So we're just going to add all these probabilities together and showing the examiner what I'm doing. There we are. So let's pop it in. So 0.048, 0072 plus 0.24, and that gives us 0.3744 for our 3 marks. Now, this is where it feeds in very nicely to part C. Whenever you're doing an A-level paper, you should try and read through the entire question. So when you look at it and go, I might need this probability to help me do this next part, because we're going to speed up this process for the 4 marks by using what we did in part B. So find the probability that Janice fails exactly once. So let's write that in. Fails exactly once. That's an important word. Given that she has finished the game. Now, as soon as I use this line, this conditional line, you should be thinking of a very important formula. That is, the probability of A given B's happened is equal to the probability of A and B divided by the probability of B. This is a formula we use again and again in this particular A-level paper. So in order to implement this with the situation we have, we want the probability that Janice fails exactly once and finishes, and you can use the intersection sign instead. I'm just going to write it in words so we have it nice and clear, divided by the probability that she finishes. Now notice the bottom we've already done in part B. We've already worked out that probability. That's equal to 0.3744 from part B. It's always the pain with these probability questions. You're using something from before, but they'll give you some follow-through marks for this. And we want the probability that Janice fails exactly once and finishes. Now, we have 4 situations where she finishes. Win-win, win-lose-win, lose-win-win, and lose-win, lose-win. The only 2 here where she fails exactly once is with 1L, basically. So we have this one and this one. So to work out the probability she fails exactly once and finishes, we add these 2 probabilities together. So we have, let's get the pen out this time, 0.072 plus 0.048. Notice how we're breaking down that situation and using the information we did in part B. So now all we do is pop this into the calculator. So we're going to do 0.0, we can just use my calculator here. So fraction button, 0.072 plus 0.048, all over, double check as always, 0.37. Oh, supposed to be careful. 0.3744. That's correct. Okay, we press the button and we get our decimal 3.205. Too many zeros. Again, so why we should always double check these things as we type it in. So let's do it again. 0.072. Again, I notice this probability was more than 1, so I know something's gone wrong. Again, always looking for reasons to double check, so it should be 0.3744. There we are. Type it in correctly. This is now a probability between 0 and 1, so 0.3205. Let's write that in. 0.3205 ... and if we round to 3 significant figures, we get 0.32123 SF, giving us here all 4 marks. Right, so you can have a look through the mark scheme. Notice I didn't take the main approach here. I took the alternative approach and worked out the individual situations, but you could work in a kind of negative approach as well. That is perfectly fine as well. And 6C, again, same approach as you see here. Again, they do give you some method marks depending on what you've used for your part B. Okay, and on to question 5. If you're liking this video so much, then please do press the like button down below and think about subscribing for more A-level maths paper 5 content. Right, so we've got a game here playing with an ordinary fair 6-sided dice. It's keyword fair, so we've got an equal probability of getting a 1, 2, 3, 4, 5 or 6. The player throws the die once. If the result is 2, 3, 4, 5, that result is the player's score and the player does not throw the dice again. If they get 1 or 6, however, then the player throws a second time and whatever that score is then the sum of the two numbers from the two throws. From that, we need to draw a fully labelled tree diagram to represent the information. So first of all, we've got our first throw. So we can either get a 1, we can get a 2, 3, 4 or 5. Notice how I'm drawing this out. This will make sense in a moment. And then we have a 6 as well. Each of those probabilities is going to be 1 out of 6. So I'm going to write that next to each of these numbers. We're not going to have much space when we're doing this tree diagram. Now, if we get a 1 here, then we get to throw again. So then we've got 1, 2, 3, 4, 5, 6. Hopefully you've got more space on your piece of paper. So we have these probabilities. Again, it's a fair dice, so each of these is going to be 1 out of 6. You can write these probabilities on the actual branches themselves. So that is also possible. And we're also going to do the same with 6 here. So 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5 and 6. And then each of these probabilities also 1 out of 6. So this is important to make sure we set this up nicely. So when we come to actually work out the probabilities, we have a clear tree diagram that we can work with. So on to part B, we've got two events, A and B, and they're defined in the following way. So A here, the player's score is equal to 5, 6, 7, 8 or 9. And event B is that the player has 2 throws. And we need to show, first of all, the probability of A. So getting 5, 6, 7, 8 or 9 is equal to 1/3. Like these show that questions, you always feel very good when you've got the answer at the end. So let's work each of these out separately. So the probability of getting a 5, 6, 7, 8 and 9. And then we're going to just add those probabilities together. Remember, 5 or 6 or 7 or 8 or 9. So we're going to be adding those at the end. Now the probability of getting a 5, well, we have two ways of getting a 5. We can either get a 5 directly. So that's the probability of 1 out of 6. Or we can do the probability of a 1 first and then a 4 afterwards. So we have two possible outcomes here. We can either do probability of a 5, which we know is 1 out of 6, or a 1 and a 4. Notice as soon as I say and in probability, I'm going to multiply the fractions. So we have 1 over 6 times 1 over 6 is 1 over 36. So we need to add together 1 out of 6 and 1 out of 36, and that will give us the probability of getting a 5, either directly or indirectly after the second throw. So we have 1 out of 6 plus 1 out of 36. And you can use your calculator to help you add fractions, but I'll do this quickly. We've got 7 out of 36. The way that we get a 6, again, we've only got a couple of ways, actually one way of doing this. We can only do it by a 1 and a 5. Notice, once I get a 6, I have to throw again, so I can't just get 6. So we just need the probability of 1 and 5. So let's write that in, 1 and 5. And that's going to be 1 out of 6 times 1 out of 6. That gives me 1 out of 36. Then we're on to the probability of a 7. Got to be careful here. There are two ways we can do this. We've got 1 and 6 and also 6 and 1. So we need to work out the probability of 1 and 6 and then add that to the probability of 6 and 1. That will give us then 1 out of 36 plus 1 out of 36. That's 2 out of 36. I'm going to put these answers in boxes because we're going to be adding those right at the end. Then we've got the probability of an 8. The only way of getting 8 is 6 and 2. So the probability of 6 and 2, that gives us 1 out of 36. And then 9 is only 6 and 3. Notice 1, we can't get to 9. There's no other number that we can add to get to 9. And that's also equal to 1 over 36. So we've got all our answers there. And so all we need to do is add them together. So the probability of A, we've got 7 out of 36, 1 out of 36, 2 out of 36, 1 out of 36, and 1 out of 36. We add those together, we get 12 out of 36, and voila, we do get the fraction of 1 over 3 when we simplify. Great feeling, we've got those 3 marks in the bag, and we can definitely make sure that we have that good understanding there. On to part C, we now need to determine whether or not events A and B are independent. So the statement for independence, if independent, and I'd write this in the exam because you might pick up a mark just for identifying this, is that the probability of A and B is equal to the probability of A times the probability of B. Now we already know the probability of A. That's equal to 1 over 3. We just did that. So the probability of B is that we have 2 throws. The only way we can get 2 throws is by either throwing a 1 or throwing a 6. So the probability of that on the first throw is getting a 1 or a 6. So that's going to be 1 over 6 plus 1 over 6, which is 2 out of 6, which is 1 over 3. So that means then the probability of A times the probability of B excuse me, is equal to 1/3 times 1/3, which is equal to 1 over 9. So keep that in mind, and now we need to compare that to the probability of A and B. So let's think about what that actually means. So A and B is the player's score is 5, 6, 7, 8 or 9 when the player also has 2 throws. So given they've got 2 throws, so let's go, we're only looking at this part now, we're ignoring that 2, 3, 4, 5 in the middle. How can we actually get 5, 6, 7, 8 or 9? What options do we have here? Well, we can do 1 and 4, that works. 1 and 5 gives us a 6, 1 and 6 gives us a 7, 6 and 1 gives us a 7, 6 and 2 gives us an 8, 6 and 3 gives us a 9. So these 6 possibilities here are the only way we have 2 throws and we get 5, 6, 7, 8 or 9. So we've got 1 out of 36, remember, to work out this one here, we just times them together, so we get 1 out of 36. Each of these is going to be 1 out of 36. How many 1s out of 36s do we have? 1, 2, 3, 4, 5, 6. So our answer here is going to be 6 over 36, and that simplifies to 1 out of 6. Notice these answers are not the same. 1 out of 9, it's very clearly not the same as 1 out of 6. Therefore, these two things are not the same, and therefore it is not independent. That is very useful to know, generally speaking, with any event. On to part D. So we want to find the probability of B given A has not happened. Remember this line is that conditional line, which we need to be familiar with. And there is a formula which we can use to work out this. This is one you really should memorize off by heart, which is the probability of B and not A divided by the probability of not A. You need to know that formula. Any probability question on paper 5, this is probably going to come up in some way. Now we know the probability of A from part B. So we know the probability of A is 1/3. Therefore the probability of not A, because all probabilities add up to 1, must equal 2/3. So we can pop 2/3 down the bottom here. Now we need to think through very carefully what the probability of B and not A is. So let's go back to our events. So the player's score is 5, 6, 7, 8 or 9. So we want not that. And they also have 2 throws. So those are the 2 things we need to focus on. So this is where our tree diagram becomes very useful. So which situation do we have where we have 2 throws? So we're looking at these big trees here. and we don't get 5, 6, 7, 8, or 9. Well, we have this option, that gives us 2, this gives us 3, this gives us 4, this gives us 5, so we leave that alone, and we also have this giving us 10, 11, and 12. So we have 6 combinations where we don't get 5, 6, 7, 8, or 9. So the probability of B and not A, well, we have 6 possibilities out of 36 in total. And so that gives us the probability that we're looking for. At this stage, we just pop this into the calculator. Again, you can do this lots of different ways. You can also use your knowledge of fractions. But if we type this in, so we have 1 out of 6 divided by 2 out of 3. This gives us 1 out of 4, giving us the 3 marks for this reasonably tricky question at the end here. So you can look through the mark scheme, so you can see exactly how they've done the tree diagram here. As noticed here, you can write the probabilities at the end, not just on the branches. Again, quite a hard thing to draw under the pressure of the exam. And we've got question B here, doing it in stages, and then 5C, and then finally 5D here, giving us 1/4 for those 3 marks. And on to our next question. So on any day, Kino travels to school by bus, by car, or on foot with the probabilities of 0.2, 0.1, and 0.7 respectively. What that means, that word respectively, is the first probability for bus is 0.2, the next one by car is 0.1, and foot is by 0.7. Now the probability that he is late when he travels by bus is x, when he's late when he travels by car is 2x, and the probability late when travelling on foot is 0.25, and the probability on a randomly chosen day Kino is late is 0.235. Find the value of x. Now tree diagrams are the way to go with these kinds of problems. Notice we have 2 events here, the way of travelling to school and whether late or not. So we'll start with the way they travel to school. So we have either bus, car, or by foot, and we have those probabilities 0.2, 0.1, and 0.7. Now for each of those, we now need to work out whether Kino is late or not late. So I'm putting L and L dash. Remember, L dash just means not late. So the probability that he's late when travels by bus is x. Therefore, not late, well, that's going to be 1 minus x. Remember, pairs of branches have to add up to 1. Exactly the same idea with the car. So probability that he is late when traveling by car is 2x. Therefore, not late is going to be 1 minus 2x. Again, those two have to add up to 1. The last one here, we have 0.25. When traveling by foot, the probability is late is 0.25. Therefore, probability of not late will be 0.75. And the probability that on a randomly chosen day, Kino is late is 0.235. So we need to find the combinations that give us that Kino is late. So we have, first of all, the probability of bus and late. So that's 0.2 times x. The probability of car and late is 0.1 times 2x. And the probability of by foot and late is 0.7 times 0.25, which we can just work out directly here. That's going to be equal to 0.175. And this means these are the 3 combinations we need to work out late. So the probability of late, so that's going to equal the first combination, so 0.2x plus 0.1 times 2x, that's also 0.2x, plus 0.175. That has to equal the probability given in the question, so 0.235. Now we just have to solve that equation. We can collect up the x's, so 0.2x plus 0.2x is 0.4x. We can minus the 0.175 from both sides. All those algebra skills we've been working on, that gives us 0.06. So we want the x on its own. So the opposite of timesing by 0.4 is dividing. So we do 0.06 divided by 0.4. So let me just write that clearly. 0.06 divided by 0.4. And that gives us the final answer of 0.15. Quite a nice 3-mark question here. Again, a lot of the marks really do count quite a lot. It's quite a small paper, so you want to be getting these easy marks in the bag. On to the second part of the question. So find the probability on a randomly chosen day. Kino travels to school by car. Given, we've got that key word here, trigger word, given. So we're going to use that conditional line, given that he's not late. So we're looking for the probability traveling by car, given not late. So notice not late is very important. We're going to use our conditional formula, which is the probability of C and not late divided by the probability of not late. You really need to know that formula. If there's anything from this video you should take away, it's that formula is crucial. Now, the probability of not late, well, we have the probability of late is 0.235. So let's just write that down. So the probability of not late is 1 minus that. Again, this idea is used again and again. Double check, yep, 0.235. So 1 minus 0.235, that's equal to 0.765. So we can pop that in down below. And now we need to work out the probability of C and not late. So we go back to our tree diagram. We're looking for this, so C and not late. So we have 0.1 times, well, we now know what X is, yeah? We now know it's equal to 0.15. So we're going to do 1 minus 2 lots of 0.15. Put this into the calculator. So we get 0.1 times brackets 1 minus 2 times 0.15, close brackets. I'm getting 0.07. Again, tree diagrams are crucial. So we have 0.07 here. And now this is just a calculator exercise. Pop it in. And I'm getting the decimal here of 0.091503. So let's round this appropriately, 0.0915. I'm doing that to 3 significant figures to give me the 2 marks on this question. So you can have a look through the mark scheme and see if you're happy with what we've covered so far in this section of the video on probability. Okay, and on to our next section here on discrete random variables. I'll often shorten this down to DRVs, an important topic that can provide quite a few marks with a good understanding. So we have 3 fair 4-sided spinners, each have sides labelled 1, 2, 3 and 4. The spinners are spun at the same time and we record the number on which each spinner lands, and we're interested with the random variable here X on the highest number being recorded from the 3 spinners. And we need to show that the highest number being 2 here has a probability of 7 out of 64. So I think the best way to think about this is in terms of combinations. How can I have the highest number being 2 after the 3 spinners have been spun? Well, one possibility here is that we could have all 2s. We could get 2, 2 and 2. So the probability of that, well, the probability of 1, 2 would be 1 out of 4, and that would be the same for the other 2 goes. So we do a quarter times a quarter times a quarter. That gives us then 1 over 64. We also have another possibility, which is we could also have 1, 1, and then we could have another 1, and then 2, and also all the combinations around that. So I've labelled this as 1, 1, 2, but we could have 1, 2, 1, and 2, 1, 1. So let's work out one of these first of all. So the probability of a 1, well, that's going to be 1 out of 4. Probability of a 1, 1 out of 4. Probability of a 2, 1 out of 4. But we have 3 different ways of doing this. If I just write these out, we can have 1, 2, 1, and we could also have 2, 1, 1 as well. So that's going to give us 1 over 64 times 3, so that's going to be 3 over 64. And then finally, we've also got the possibility of having 1, 2, 2, so that's also a possibility. Again, we've also got different combinations of this. We could have 2, 1, 2, and we could also have 2, 2, 1. So again, very similar to what we just did here. Again, the probability of a 1 is a quarter, probability of 2 is a quarter, probability of another 2 is a quarter, and we have 3 possibilities of this. So that gives us then 3 over 64. Again, these are all the chances of getting 2 as our largest number. Notice no 3's here or no 4's. So probability of x being 2, i.e. the highest number being 2, is just these 3 added together. So 1 over 64 plus 3 over 64 plus 3 over 64. That gives us then 7 over 64 in total, which is the answer given in part A. Now we know this, we can put this into our probability distribution table, which has been done for us. And now we need to work out the rest of the probability distribution table here. So let's start with the easiest one here, which is going to be this one here. So the highest number being 1. Well, there's only one way of that happening, and that's if we get 1, 1, and 1 on the 3 spinners. As soon as you get a 2 or a 3 or a 4, that's going to be the biggest number. The probability of 1, 1, 1, that's going to be 1 over 4 times 1 over 4 times 1 over 4. So that gives us 1 over 64. So again, start with the easiest, and then hopefully we can work out the hardest without having to go through all the combinations. Notice probabilities always have to add up to 1. We talked about this in the probability section. So if I want to work out the missing probability here, well, what I need to do is do 1 minus, and then all the others added together. Again, probability distribution table always adds up to 1. So if we simplify this down, we've got 1 plus 7 plus 19. Again, if you're very afraid of making a mistake, of course you can use your calculator in the exam. So essentially here we're doing 27 over 64 and then 1 minus this. So 1 minus 27 over 64. Again, don't have to do anything complicated with fractions. We then get 37 over 64. Again, you should always do a double check to make sure that these do add up to 64 out of 64 or add up to 1. Now, on another occasion, one of the fair four-sided spinners, so just one of them now, is spun repeatedly until a 3 is obtained. And the now new random variable, which is y, is the number of spins required to obtain that 3. And the first time we need to work out the probability of y being 6. So in real languages, it takes 6 times to get a 3. The best way of looking at this is essentially a tree diagram. So we can either get a 3 or not get a 3. The probability of a 3, well, it's a fair spinner with one of each, so we have 1 over 4, and therefore the probability of not a 3 is 3 over 4, and that's our first spin. If we do it again, then we have 3 or not 3. So we have 1/4 and 3/4, and essentially we just keep going with this process until we get 6 times to get that final 3. So to work out this probability, we need to do 3/4 times 3/4 times 3/4 times 3/4 times 3/4, and then on that 6th go, then we get that 3, and that's going to be 1/4. So we can write this actually in a nice neat format. 3/4 to the power of 5. 5 times we don't get that 3, but then that 6th time we do, so that's where our quarter comes in. Again, we could put to the power of 1 if that makes it make more sense. So we pop this into the calculator. So we have 3/4 to the power of 5, and then times a quarter. And that's going to give us some horrible fraction, but as a decimal, which generally on the A-level maths paper 5 they prefer, 0.59326. And again, we always round this to something sensible. 3 SF, 3 significant figures, makes a lot of sense to get our 1 mark here. And now we need something a little bit more complicated, which is the probability of y being greater than 4. So in other words, it takes more than 4, so be careful with the inequality here, more than 4 times to get a 3. Sometimes it's useful to write this out to get a 3. So the way I generally work this out is working backwards. So the probability of y is greater than 4 is the same as 1 minus the probability of y equals 1 plus probability of y being 2, probability of y being 3, and don't forget we also have to add in the probability of y being 4 because we're looking for greater than 4 here. So the probability of getting on the very first go, that's a nice easy one to calculate. That's just equal to 1/4. Then y is 2, that's going to be 3/4 times 1/4, and then 3 times 3/4 all squared because we had it missed 3 times, but then we got 1/4, and then finally 3/4 all cubed times 1/4 to represent 3 times we missed it, the 4th time we got it, but we're looking for greater than 4 here. So we've got the calculation set up. Let's go to my calculator. So the key thing with this is just to make sure we're nice and careful as we type this in. So 1 minus, open our bracket. First of all, we have 1/4 plus 3/4 times 1/4. So where the calculator is helpful, giving you different coloured brackets so you know you haven't used too many brackets. Then we've got, let's pop in 2 lots of brackets here actually. So 3/4 squared times 1/4. And just checking we get everything as we want here. And then we've got plus 2 brackets 3/4 cubed, where your nausea calculator is very useful. And then we pop in 1/4, close bracket. So we've got everything closed, press equals, and then we get our final answer of 81/256. Generally, we prefer these as decimals, so we get 0.3164. Let's pop that in, 0.3164, ... and that gives us then 0.31623 SF, again using that standard rounding that we've done before. So you can have a look through the answers here, so all the different ways that we've done this. Lots of different ways of doing method A. I've gone with, I think, the most straightforward approach, kind of very permutations, combinations approach. Again, that's the section 1 of the video. And then you've got 4B, 4C there, and then finally 4D. Can take this approach as well. I've taken the alternative, but again, lots of different ways to attempt the same question here. Okay, on to this question here, question 2. So a fair 6-sided die has the numbers 1, 2, 2, 3, 3, 3 on its faces. The die is rolled twice, that's important. The random variable x in this case denotes the sum, which is quite typical, of the 2 numbers obtained. We want to draw up our probability distribution table. So we have our x and our p. Let's think about all the different outcomes that are possible here when we throw it twice. So the minimum we can get is 2, so 1 and 1. And the maximum we can get is 3 and 3, which is 6. So we've got 2, 3, 4, 5, and 6. And at this point now, we just need to work out the probabilities for this. Now the first one is, I think, fairly straightforward. We've got, first of all, 2. So the only way we can get a 2 is a 1 and a 1. So that would be 1/6 times 1/6, which is 1/36. No other way of getting 2 with 2 dice. So we have 1/36, popping that in. Let's think about 3 next. So the way we can get 3, we can either do 2 and 1, that way round. We can also do 1 and 2 as well. So we need to count both here. So let's think, the probability of a 2, that's going to be equal to 2 out of 6, then times 1 out of 6, So that's 2 out of 36. Other way round will just be the fraction swapped. So it gives us 2 out of 36. So combined here, we then get 4 out of 36. So that goes into here. Next one, so let's look at 4. The only way we can get 4 here is the probability of... we can always get 3 and 1 as well. Okay, so 2 and 2 first of all. And then we've got probability of 3 and 1 and 1 and 3. Okay, we can do this any way around that we like. So let's do 3 and 1. So that's, we've got 3 out of 6 times 1 out of 6. That gives us 3 out of 36. Then we've got 1 and 3 the other way round. So that gives us 1 out of 6, 3 out of 6. So that's 3 out of 36. And then we've got 2 and 2. So that gives us 2 out of 6 times 2 out of 6. That's 4 out of 36. This can't be swapped because the numbers are the same here. And then we just add these results together. That gives us 10 out of 36. Okay, this is where we have to decide, is it easier to work out 5 or 6 here? We'll go with, I think, the 6. So looking for this one. Now, the only way we can do that is the probability of 3 and 3. Yeah, this I think is a bit easier. So we have 3 out of 36 times 3 out of 36. Again, there's no conditionality here. That's important. So that gives us 9 out of 36. And instead of having to work out the last one directly, we can use the idea that the table always adds up to 1. So we have 10, 9, 4, and 1. That gives us then 24 out of 36. Therefore, this needs then to be 12 out of 36. So you can always be a bit lazy with the last one. You can just use the idea that probabilities add up to 1. That's an important fact to remember. Okay, on to this part, and this is where you do need your formula sheet. So we're looking for the expected value and we're looking for the variance. Now, the formulae, you always have this on your formula sheet. So I've got this here for you under our section here of discrete random variables. We're going to be using these two formulae, so the expected value formula and the variance. Notice the variance requires the expected value, so you want to do expected value first and then the variance. And what we're looking for here is the sum of x times p, so x times the probability. With fractions, I'll show you the way that I generally approach this. So if we go back to our question here, the way I generally do this is focus on the numerators, because I'm always going to have to divide by 36 at the end anyway. So I'm going to be focusing on these parts here. So in order to work out the variance, the expected value, which on the formula sheet, always worth writing this down. So we have xp. So we know it's going to be out of 36. And then we just times the numerators together. So we do 2 times 1 plus 3 times 4 plus 4 times 10 plus 5 times 12 plus 6 times 9. Again, this is all going to be out of 36 here. So again, we just put this into the calculator. So let's get the calculator ready here. So we have 2 times 1. This paper is really a test of your calculator skills and just making sure you don't make any silly errors. I remember when I was doing A-level a long time ago. Again, paper hasn't really changed much in the last 10-15 years. And the key thing was just making sure you put things in the calculator correctly. You don't want to miss out on marks unnecessarily. It took me a bit of practice before I really got to grips with this, but a long time ago now. So over 36, if we work that out, we get 14 over 3. Generally, I like these things as decimals. So again, easiest way of doing this is just pressing the SD button. Again, don't have to use too much brain power. So 4.6666. Okay, so let's pop that down. 4.66 dot dot dot, and that just rounds then to 4.67. Useful to have it as a fraction because we're going to use this for the variance formula anyway, so we do need to keep that in mind. Right, so now on to the variance. Now always worth to write down the formula from the formula sheet. So now we've got the sum of the x squared, so that's going to be important, p, minus the expected value squared. So this is the trickiest part, the sums of the x squared p's. What does that actually mean? So easiest way of doing this is just popping x squared and just squaring the x terms here. So we get 4, so 2 squared is 4, 9, 16, 25, 36. And again, we're using the same sort of highlight method here. Let's use a slightly different color. So this time we're going to be multiplying these 4 9s with the numerators here. So again, highlighting, just make sure you keep track of exactly what you're multiplying and working out. So let's then work this out together. So we have, first of all, over 36. So we know it's going to be over 36. That's not going to change. So we have 4 times 1 plus 9 times 4. So notice all the x values have been squared here. 16 times 10 plus 25 times 12, 36 times 9, double check, yeah, it's all good. And then we minus the variance squared. This is where putting it as a fraction is quite useful. So 14 over 3 squared. Okay, we've got everything here. Now let's go to the calculator. It's really good if you do this with me, so you're getting that practice as we go through. So any calculator will do here. You don't have to have a graphical one. So let's look through. So we start with our fraction. We have 4 times 1, brackets, plus 9 times 4, plus 16 times 10 plus 25 times 12 plus 36 times 9, okay, all over 36, and then we want to subtract the variance squared, expected value squared to get the variance. 14 over 3 all squared. Press the big button. After all that, we just get a fraction 10 over 9, which is the same as 1.11. So let's write that down. So we get 10 over 9, same as 1.11. Again, we've done this to 3 significant figures for both here. Okay, so you can go through the mark scheme. Again, you could also take this approach instead. So if you don't have fractions, for example, all you have to do is just 2 times this, plus 3 times this, plus 4 times this, 5 times this, and 6 times this. So if you want to work with decimals, that's the approach that you would take for the expected value. Again, but you can look through the mark scheme here and just check that you're happy with all the details that I've gone through, working out expected value and working out the variance here as well. Okay, and on to the normal distribution part of this video. So you're going to need a very important part of your formula sheet in order to work with any normal distribution question. And it's probably one of the first times you've actually used tables to work with a particular function. Back in the day, we used to use these things quite a lot for logs and lots of other things. Normal distribution is one of these where we still use them. So you should have this table familiar to you. Also, the critical values of normal distribution is also a very nice sort of shortcut as well to use too. So we're going to be using this a little bit later on, so do keep this in mind. Right, so the weights in kilograms of bags of rice produced by Anders have the distribution of n, so n stands for the normal distribution, Again, in this video, we're not looking at any other distributions apart from binomial, but you'll think like Poisson, for example, in statistics 2, you'll see a PO for that. And whenever we get a normal distribution, then we always get the mean value. So the first value is always the mean, the 2.02. And the 0.03 itself, that's what's known as our standard deviation. If we square the standard deviation, then we get what's called the variance. Now, we want to find the probability that a randomly chosen bag of rice produced by Anders weighs between 1.98 and 2.03 kilos. So we've got our normal distribution already, and what we're looking for here is the weight to be between 1.98 and 2.03. So this is what we're looking for, and the standard way of doing this is by standardizing our normal distribution. So let me just go through the standardization process. So in order to standardize anything, we take whichever number that we have, we minus the mean, and then divide by the standard deviation. This then allows us to use the table to actually read off the values that we're looking for. Again, we're going to do a couple of examples like this, so that seems quite confusing at first. Don't worry, it'll get better as we go through. So we want to standardize this, so we take the 1.98, we minus the mean, so that's 2.02, and then divide by the standard deviation, which is 0.03, not squared, but just 0.03. We do exactly the same to the 2.03, so we minus the mean, and then we divide by the standard deviation. That'll give us two particular values. So if we type this in, we get 1.98 minus 2.02, and then divided by 0.03. That gives us then minus 4/3, or generally write this out as a decimal, minus 1.33 recurring. We do exactly the same to the other side, so 2.03 minus 2.02, then divided by 0.03. That's going to give us 1/3, so that gives us 0.333 recurring. So we have our standardized normal distribution here at this particular point, and now essentially we want to find the area in between it. Think of it like integration limits here. So we get the normal distribution at 0.333 ... minus the normal distribution at minus 1.333. Now generally we can't work with negatives within the normal distribution here using the table, so we do a little bit of a change here. So we have 0.333 ... Now we can use the formula given here. If we get negative values of z, which we've got here, you can write it as 1 minus the positive version of it. So we can then go minus, open brackets, 1 minus normal distribution at 1.33 ... Okay, so we have the normal distribution we want to work out here. Now it's all about our understanding of the table. So if we go back to this, we want 0.333. That was the first thing we want to look at. So we find 0.3, then we find the 3 here, and then we want another 3. So we have this add 11. So let me explain what this means. We look at this first. So this is 0.6293. And then we want to add 11 to this, so that's the last two digits. If we add 11 to that, we'll then get 0.6304. So what this means is that the normal distribution at 0.333, that's equal to 0.6304. We're going to do a very similar approach with the normal distribution at 1.333. So we go to our chart here, we have 1.3, we're looking for 3 again, and then we want 3 here. So we have 0.9082. Always look at this number here first, and we're adding on 5 to the last digit, so that gives us 0.9087. So we pop this in over here. And at this point, once I've got those values and used the table correctly, then I just plug this into my calculator. So 0.6304 minus 1 minus 0.9087. And that's going to give me, as a decimal, 0.533 0.391. Again, we always round, of course, to three significant figures. So our final answer to 3SF will be 0.539. Okay, on to the second part, which is a very typical thing they could ask you working with these standardized normal distributions. So the weights of bag of rice produced by Binders, so different company here, are normally distributed with mean 2.55 and standard deviation of delta here. So we can write this down then as 2.55 as our mean, and then we have whatever the standard deviation is here squared. In a random sample of 5,000 of these bags, 134 weighed more than 2.6 kilograms. So what we're saying here, probability of x being greater than 2.6 here is equal to 134 over 5,000. That's the sample that we're looking at here. I usually put these things into decimals. So that means 0.0268. Okay, so we've got that there like so. Now we just need to put it into a standard normal distribution. This time though, we actually have the result, but we don't have the standard deviations. This is another variant of question they could ask you here. So what we want to do is use the formula that we did before. So this was the formula of minusing the mean divided by the standard deviation. So we do the same thing here. We have 2.6 minus 2.55 divided by the standard deviation, and that's going to give us 0.0268. However, notice our table, which I haven't mentioned so far, it only gives us values for when we have z is less than or equal to small z, so keep that in mind. So in order to use this correctly, we essentially need to flip. So if I'm going to flip this, and you've seen this idea already in this video, minus 2.55 over theta. So if I switch this sign, I need to do 1 minus this. Remember, you think about a normal distribution. If we're up to here and we're looking at this part, if I want to reverse the sign, well, I just need to do 1 minus what this part was before. So if I do that, so 1 minus 0.0268, watch out for this, you get 0.9732. And this is where we use the table in a slightly different way. If we simplify this down, we get 0.05 over little delta. So 0.9732. We go to our table. What we're looking for is 0.9732. So this number, the result, we're looking for in the table and then work backwards. So can we find it? 0.9732. Makes your eyes go funny looking at this. 732. Yep, I found it. It's this one here. So that's going to be 1.93. Okay, so equal to 1.93. At this point now, we've just got a straightforward equation to solve. So then we have our standard deviation is equal to 0.05 divided by 1.93. Bit of equation solving, and then we get 0.05 divided by 1.93, and that gives us 0.025906. and that's equal to 0.0259 for our standard deviation, again to three significant figures for our 4 marks. So this kind of question, working backwards to find the standard deviation, is very common. Again, we're going to do a very similar question in the next slide. If you want to look through the answers, all the answers are here for you. So question 4A and 4B. Right, you're going to need this chart again, so I've got it here ready. So this time we've got the weights of male leopards in a particular region are normally distributed, that keyword. As soon as we see that, we know we're doing this process with a mean of 55 kilos and standard deviation of 6. So before I do anything, I'm just going to write this down. So 55 is the mean, 6 squared here to represent the variance, and find the probability that a randomly chosen male leopard from this region weighs between 46 and 62 kilos. So we're looking for between 46 and 62, like so. Now we want to do our standardizing procedure, so we can use our table a bit later on. So that means then we want to then do 46 minus the mean divided by standard deviation to both of our limits here. So 62 minus 55 all over 6. Let's work out what that's going to look like. So 46 minus 55 divided by 6. That gives us negative 1.5. Is x, and 62 minus 55 divided by 6. That gives us 7 over 6, which is 1. Now we're going to work to 3 decimal places with our table. So 1.167. And you'll see why I've rounded it specifically to that in a moment. Okay, so now we need to formulate how we want to work out the normal distribution. So we're going to be doing the normal distribution at 1.167, again, minus at minus 1.5. Now remember, because we've got a negative just like before, we need to switch it around. So we have minus 1 minus at positive 1.5. So we need to work out these two things using our table. Let's start with 1.167. So 1.1 is here. We want 6, which is going to be this. And then we want the 7 in this row, so adding on 14. So we have 0.8770. We're adding on 14. So we have 0.8784. So that's going to give us our value for 1.167. So this is going to be 0.8784. And now we do 1 minus. Now the value at 1.5 exactly. Okay, that's much easier to read off. We can just read off 0.9332. So 0.9332. At this stage, we now just put this into the calculator. So 0.8764 minus brackets 1 minus 0.9332. And that gives us the value of 0.8096. And it's going to round to 0.810 to 3 significant figures. Okay, so we've got our value here. On to question 4b. The weights of female leopards in the region are normally distributed, again that key phrase, with mean of 42 kilograms and standard deviation of this kilograms. It's known that 25% of female leopards in the region weigh less than 36 kilos, and find the value of the standard deviation. Okay, so we know that this is equal to 25% or 0.25. This is where the critical values at the bottom, which we haven't really talked about, really come very important. So we're told here that at this particular probability, so if we take here at small z is equal to say 0.75, then the p-value, the z value has to be 0.674. Notice, because of how the normal distribution works, so we have this symmetry in the middle, essentially 0.75 will be exactly the same as 0.25, so we can still use the same value. So our z value at this particular point at 0.25 is equal, depending on whether it's on the left hand side or the right hand side, plus or minus 0.674. So this is quite a nice way to actually get to this straight away. Of course, we have to standardize the left hand side here. So if we standardize this, we have 36 minus the mean, which is 42, divided by the standard deviation, which we don't know. And this is going to equal plus or minus 0.674. So if we do this, we get minus 6 over the standard deviation. Now, in order to get a positive at the end, because the standard deviation, we only work in positive numbers here, this needs to be a negative 0.674. So then we can just easily work out that the standard deviation will be minus 6 over minus 0.674. Pop this into the calculator. So minus 6 divided by minus 6.674. That gives us 8.902 ... And again, we can round to 3SF 8.90 to 3 significant figures. So a slightly different approach to what we did in the previous question, where we can just use the Z value given at the bottom of the formula sheet. And that helps us a lot then to work out standard deviation relatively quickly. Okay, so there's the mark scheme for question 4A and 4B. Again, this video is usually a very quick 2-hour look at all things paper 5. If you want more detail on this kind of video, because I know it's one of the harder topics on the course, then do let me know in the comments below if you want me to do a all of normal distribution style video, which goes in much more depth than this particular section.